Hey, what's up? It's your old pal, Mr. Cook. We're going to go through this review here, and we just got through the first four problems, so let's start with number five and keep going. So in number five, looks like we got a brand new limit, and we're evaluating what happens as x gets really, really, really big. So it kind of depends on how your teacher showed this. This is really just like an algebra 2 trick. You can tell what's going on with the limit based off of just the fact that the degree in the top is equal to the degree in the bottom. So it's like a pretty easy problem to work through. Let me think. So there's a couple ways that I've been shown how to do this. One way that I do it is by finding the term with the biggest degree and then dividing by that biggest degree. Okay, so this is one way to do it. You can always just divide by that biggest degree. So what I would do is I'd say that this is equal to, first off, I'd look for the term with the biggest degree. In this case, it's x squared, right? If there was like an x to the third, I'd say x to the third is the biggest degree and so on, but x squared is the biggest. So what I'm going to do is I'm going to take the limit as x goes to infinity. And what I'm going to do is I'm going to take that 5x squared and also that x squared plus 2. And what I'm going to do is I'm going to multiply the top and the bottom by 1 over that largest degree, x squared. Okay, so 1 over x squared. And I can do that because the x values are going to be gigantic. They're not going to be 0, so this is okay. So then what I do is I would distribute all that stuff in there, and I get the limit as x goes to infinity of, and then it'd be 5 times x squared, and then times 1 over x squared over, and then if I distribute 1 over x squared to both of those, I get x squared times 1 over x squared, and also 2 times 1 over x squared. All right, and then x squared times 1 over x squared is just 1, so this turns into the limit as x goes to infinity of x squared and the 1 over x squared cancel out, so I just get 5 in the top. And then x squared times 1 over x squared is just 1, and then plus 2 over x squared. Now as x gets gigantic, this thing basically goes down to just 0, so that means that the limit is going to end up being 5 over 1, or just 5. Now, depending on if your teacher allows this or not, there's also a shortcut for this. And here's how the shortcut can go. What you do is you look at the rational function, and then you look at the degree in the top and the degree in the bottom. So what we would say is, like, in the numerator and denominator, denominator, have the same degree. So that means that, like, the largest degree terms are the ones that are going to dominate the expression. So that means that you can just say that the limit as x goes to infinity of 5x squared over x squared plus 2, it's just going to be dependent on those terms, that have the biggest x power. So 5x squared and x squared. And what you do is you just compare the coefficients on those biggest terms. So that means it'd be 5 in the top and then 1 in the denominator. So 5 would be your limit for this one as well. So you can do kind of a shortcut if you do that explanation on it as well. And again, I would just default to what your teacher says. So if you saw something like this done in class, do that. If you've seen something like this done in class, do that instead. All right, let's take a look at number 6. So with number 6, it says to find the limit of this expression analytically. So analytically means that what we're going to do is, like, try to simplify the expression. Okay, so we're going to factor and then try to simplify and make the expression really easy to work with. So we're going to need to know some factoring rules for this. One rule that's really important to know, like to just have as a good thing in your bag of tricks, is the cubic expression. So whenever you see a cubic, there's this thing called the difference of cubics and the sum of cubics. And here's how they go. If you have two cubic expressions, so two cubed values, and they're subtracting from one another, then this expression can be factored in the following way. It can be factored to become a minus b, and then times parentheses a squared, and then it's plus, wait, is it plus or minus? I think this one's plus and plus. So plus ab plus b squared. And then if it was a to the third plus b to the third, so if it was the sum of two cubes, then it becomes a plus b, and then it would be a squared minus ab plus b squared. B squared. Let me double check. I'm going to look on my phone real quick and see if that's right. Just like Google it real quick. Yeah, that's right. Those are both right. So if you know those like difference of cubes and also the sum of cubes, factoring a cubic expression is really, really easy. You can just kind of like jump right to that, conclusion. So that's what I'm going to do. And I noticed that both of these are cubes almost. So I'm probably going to use this one right here. So I'm going to get rid of the sum of cubes, and I'm just going to use the difference of cubes expression. All right, so first things first, I look for common factors to factor out of both the numerator and denominator. So that's like the first thing I do. I'd say that the limit as x goes to 3. So I notice that I have a 5 here, and 135 is divisible by 5, so I divide out the 5. So I get 5 times parentheses x to the third minus, oh gosh, what's that going to be? 27? Yeah, 27. And then 3 and 27 are both divisible by 3, so I take a 3 out, and I get x squared minus 9. Okay, then, I'd factor it a little bit further. So this difference of cubes, in this case, like, if I want to make it look like this, x to the third minus b to the third, that means that a is equal to x and b is equal to 3, because 3 to the third is 27. So then if I just like plug it into this relationship, here's how it would factor to look. So I'd have the limit as x goes to 3 of 5 times parentheses, and then it'd be a minus b, so x minus 3 times parentheses, and then it's going to be a squared, so x squared, plus a times b, so that's going to be 3x, and then plus b squared, which would be 9. All right, so that's the top part. And then in the bottom part, I noticed that this is a difference of squares, and that one's a really easy one to factor. That's going to be x minus 3 and then x plus 3. And notice that x minus 3 in the top and x minus 3 in the bottom, those would cancel out. That's a removable discontinuity. So that means that we would end up with the limit as x goes to 3 of 5 times x squared plus 3x plus 9 all over 3 times parentheses x plus 3. Then we go ahead and plug 3 in for our x value because we shouldn't have any discontinuities any longer. And then we would get our answer. And I would just leave it like this, 5 and then 3 squared plus, 3 times 3 is 9 plus 9 all over 3 times parentheses 3 plus 3. I mean, actually, you know what? I'll just like simplify it. Who cares? So it'd be 5 times 9 plus 9 plus 9 is 27. And then 3 plus 3 times, 3 times 6 is going to be 18. And I know that 27 and 18 are both divisible by 9. So this becomes 5 times 3 over 2, which would be 15 over 2. So 15 over 2 would be my limit overall. All right, so there you go. There's number 6. Now we got a couple of really quick ones, number 7 and number 8. So yeah, let's take a look at these ones. So for number 7a, we've got the limit as x goes to 6 on the left-hand side of this graph. Okay, so if you have your graphing calculator, it's telling you to find each limit graphically. So let's go ahead and do that. All right, so here's what I would get. If I graph this thing out, so let's let y equal square root of 36 minus x squared on our graphing calculators, and let's see what it looks like. Okay, so graphing calculator, graph it out. So we've got the square root of 36 minus x squared. All right, graph it out. And there's what it is. It looks like it's going to be a half of a circle. And yeah, indeed, up at the top it goes to 6, to the left and the right it goes to 6 as well. So here's how my graph looks. And this will be part of your work, by the way. Show the actual graph when you need to show it graphically. All right, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, and then just like graph it as best you can. There we go. There's my little half circle. All right, so let's see what happens. So as x gets closer to 6 from the left-hand side, it looks like it's going this way, and then it all of a sudden gets over to there. At 6, it's going to be 0. So as x gets closer and closer to 6 on the left-hand side, the y value is going to be 0. So that means that my limit is going to be equal to 0 for that one. All right, let's see what happens as x comes in from the right-hand side. Now, here's what's interesting about it. If I pick any number that's greater than 6, everything falls apart. Like, watch this, okay? So there is no right side on the graph, first of all, because it's half of a circle. No points exist beyond x equals 6. But watch what happens if I do try to plug in something just marginally bigger than 6, like maybe 6.1. Then what I would get is the following. Square root of 36 minus 6.1 to the second power. And that is going to be a number that's more than 36, right? So if it's 36 minus a number bigger than 36, I'm going to get the square root of a negative. Can I take the square root of a negative? No, not with the real numbers. So that means that this is one of those cases where since there's no value over to the right at all, This is actually a limit that does not exist for the right-hand side. All right, now let's talk about part C of number 7. So in part C, it says, all right, now find the limit as x goes to 6, as it actually goes to that value of 6. Well, here's the deal. The limit is not going to be able to exist at that point. And the reason why is because the limit as x goes to 6 on the left-hand side of this function has to be equal to the limit as x goes to 6 on the right-hand side of this function. But there is no right-hand side, so it does not exist. So since these are not the same thing, does not exist, not the same as 0, I got news for you, the limit does not exist. So that means that for this one, the limit also does not exist. All right, so there you go. There's number 7, and now we're on to number 8. If the piecewise function f is equal to that stuff, use the definition of continuity, so showing all 3 steps, to determine if f of x is indeed continuous at f equals -2. So for that to be the case, here's the 3 steps that you need. Number 1, you need to know that the actual point exists, and it's some number. So f of -2 needs to actually exist. It needs to be equal to some number. The next thing that you need to show is that the limit exists. So the limit as x goes to -2 on the left and the right-hand side need to be the same. So the limit actually needs to exist. Okay? And then the third step is that you need to show that the function, the actual number, the point where the function is located, is equal to the limit as x goes to that point. So that's the 3-step process that you need to show. And I would recommend doing it in this order because then, it kind of it increases the difficulty. Well, actually, it's kind of, I guess, oscillating. This part's really easy. This part's a little bit tougher sometimes. And then this part's really easy because you're just comparing. So yeah, let's start with the first one, f of -2. So what actually happens when x is equal to -2? I can tell you what happens when it's not equal to -2. That's how, I would use this function when it's not equal to -2. However, if it is equal to -2, that means that I would use this function, which is just -9. So no matter what happens, when f is -2 and it actually is -2, the y value is -9. So that's part 1. Find out what happens when, x is actually at that location. The next thing is my limit. So now I need to find the limit. So I'm going to need a little bit of space here because I need to figure out what's going on the left-hand side and what's going on the right-hand side of this limit. Okay, so I start off with the limit as x goes to -2 on the left-hand side of the function, 4x squared plus 7x minus 2 over x plus 2. And I have a sneaking suspicion that this is going to be a removable continuity, I think. And I better hope that that's the case because otherwise, I'm going to get different left and right-hand side limits possibly, and that could blow up. It could be a DNE situation, and then it won't be continuous any longer. But let's see what happens with this. Okay, so let's see. Let's factor the top part because I have a feeling that I'm going to get an x plus 2, and I bet it's probably going to factor out. So let's see what happens. So I need to find numbers that multiply together to be, let's see, 4 times -2. I need to find numbers that multiply together to be -8, and then add together to be the middle number, 7. That would be, let's see here, +8 and -1 would be the ones that I would use. So that means that if I took that 4x plus 8 and a 4x minus 1, if I divided out the common factor there, 4, I would get x plus 2 for one of the factors, and then the other one is 4x minus 1. So that means that this top part will factor to become, let's see here, x plus 2, and then 4x minus 1. And then in the denominator, I've got another x plus 2, and of course, it's going to simplify here in a second. Okay, so there we go, factored, and that's what I end up with. Okay, if the x plus 2's cancel out, then that means that this is equal to the limit as x goes to -2 on the left-hand side of the following. If the x plus 2's cancel out, it's just 4x minus 1. And then if I just plug in -2 for this, I get -2 times 4, and then minus 1, and that's fine. That's going to be -9. So that looks good so far. Now let's take a look at the right-hand side limit. So that's going to be the limit as x goes to -2 on the right-hand side. And I'm basically just going to redo all the steps that I just did because I showed this analytically, and it worked out pretty well. So 4x squared plus 7x minus 2 over x plus 2. And then that's going to be equal to the limit as x goes to -2 on the right-hand side of, factoring again. I got x plus 2 and then 4x minus 1 over x plus 2. And then the x plus 2's cancel out. And so that leaves me with the limit as x goes to negative 2 on the right-hand side of 4x minus 1 again. And if I plug in negative 2, I end up with negative 9 one more time. So this is wonderful because I've just shown, let me get rid of a lot of this extra stuff, but I've shown that the limit on the right-hand side is equal to negative 9. And I've also shown that the limit on the left-hand side is equal to negative 9. So if these two limits are the same, the left and the right-hand side, then that shows me that the limit as x goes to negative 2, on both of them, because it meets up on the left and the right-hand side of this function, f of x, is going to be equal to negative 9. And that's fantastic news, because I just learned that the limit exists, and it also is going to be negative 9. So this is really important. Okay, so I'm going to erase some of this stuff, but I do need all of that work that I just showed to get credit for this problem. So I know what the function is. I now know what the limit is over here. So now my last step is to show that the limit is equal to the actual function value. So, for my last step, here's what I do. I write f of negative 2 is equal to negative 9, which is equal to the limit as x goes to negative 2 of f of x. And so therefore, this is what I write out. Therefore, f is continuous at x equals negative 2, for this function. Okay, so therefore, and I guess I could say by the definition of continuity. It depends on how specific your teacher is about this, but you might not need that sentence on there. I don't know. I'd kind of ask them if I were you. Okay, there we go. So I wrapped up the first page. We just got through number 8, and I think that's a good place to stop for this video. All right, so I'll see you on the next one. Bye-bye.